Welcome everyone to the webinar on the optimization of a high-power electric traction machine, co-presented by ESTECO and Powersys Solutions, with special thanks to JSOL Corporation. I'm your host, Adarsh, from ESTECO North America, and I have with me Dheeraj Bobba from our partner, Powersys Solutions. Thanks also to Sainan at Powersys Solutions for helping putting this together for today. So electrification is becoming a prime driver in sustainable mobility. Key to electrification is the design of an efficient electric traction machine. And in today's webinar, we will touch on the topic of how optimization and statistical data analysis can help you design better traction machines. To highlight this approach, we are partnering with Powersys Solutions, who have an expertise in electromagnetic simulations using the software platform JMAG developed by JSOL Corporation. I will begin by going over the agenda of the session for today. It will take us through a brief introduction of our companies. Then following that, Dheeraj will give us an introduction to the Synchronous Reluctance Machine, its design features, and how it can be set up to be simulated within JMAG. After that, I will cover how the JMAG simulation can be automated through the integration capabilities available in modeFRONTIER. Further, I will then take you through the optimization study and then pass it back to Dheeraj to discuss the optimized SynRM design. Through the webinar today, if you have any questions or comments, feel free to type them in the WebEx Q&A box, and we will answer them at the end of the session. So just to get started, as an introduction to ESTECO and the technology that we deliver, we primarily focus on the areas that are on the slide here. So we aim to provide solution in the multidisciplinary design optimization space, integration and process automation. Those are the prime areas, but not only that, we add value by providing solutions for engineering data intelligence, distributed execution of your simulations, and the data management that come out of your simulations as well. Moving on, we provide this technology through two major software platforms that ESTECO develops and provides. Primarily the modeFRONTIER desktop platform, which is a process automation and optimization platform, and the Volta Enterprise platform, which is an extension of modeFRONTIER. For the study today, we used modeFRONTIER, and that is what we will be focusing on today, but ESTECO has two software platforms. Now, I will pass the ball to Dheeraj to introduce Powersys and introduce the webinar content today about SynRM machines.
Thank you, Adarsh. This is Dheeraj, and I work as a senior electromagnetic design engineer at Powersys. So firstly, I'll start with the introduction to Powersys and our company and what our platform is about, and then I'll go through the reluctance machine design. So Powersys is an engineering software and services company that focuses on providing global solutions in the field of electrification and primarily on EV and grid applications. So we have about 8 offices and over 55 employees globally, and our North America locations are in Rochester Hills, Michigan, as well as in San Diego and San Jose in California. So as I said, EV and grid are our primary focus, and for today's webinar, we'll be looking at the EV platform, and that is built around JMAG, which is a electromagnetic finite element analysis tool. And this JMAG platform is built by partnering with several other technical partners. And of course, one of them is modeFRONTIER in the field of optimization. So this is where today's webinar will be focused on. To quickly give an introduction of JMAG as well, JMAG Group is part of JSOL Corporation, and they are headquartered in Japan. They have been established for a while now in 1980, and it's driven by the practical needs of customers in the field of electromagnetic analysis. The tool itself is kind of tailored and built around electric machines, but there's a lot of application needs that it can meet. Here's a quick example or a short list of applications that are at the bottom here. Motors, generators, transformers, actuators, induction heating, wireless power transfer, etc. So with that, let's jump into the main topic, electromagnetic design of the synchronous reluctance machine to begin with. To understand that, first let me start by explaining what a synchronous reluctance machine is. So the image here is showing a flux path in red lines through a magnetic material, which in this case is steel. And the outer portions are static, and the center piece is called the rotor, which can rotate on its center axis. And in the first image and the third image, the flux or the rotor position is directly aligned with the flux path and orthogonal to the flux path respectively. So these we will call direct axis with the aligned and quadrature axis when it's orthogonal. And in both cases, there is no torque developed on the rotor piece. That's because the flux path is symmetric and the reluctance doesn't really play a role. But anywhere in between, when it's not aligned, the reluctance variation with the air and this magnetic material will develop torque, which will try to push this rotor piece to align with the stator pieces. So this one is shown in a linear fashion. We can also convert that onto a more circular or cylindrical portion, which depicts an electric machine. And here, with the stator winding, we can inject two different currents, D-axis current and Q-axis current, which produces corresponding fluxes in the D and Q axis. With that, we can also define something called inductance, which is a function of the rotor design and the stator and rotor air gap. In the axis where the flux can flow freely or less reluctance is the high inductance axis, and the other one will be the low inductance axis. Here I'm also including a torque equation. The key point here is that the torque amplitude or magnitude of torque is dependent on the difference between this D and Q axis inductance. This is for a single phase example. We can also convert that to a three-phase machine where the phases are sequentially turned on and the magnetic field or electromagnetic field from the stator is rotating and the rotor is trying to continuously catch up with the field in a synchronous fashion. And this is why we call it synchronous reluctance machine. Ideally, synchronous reluctance machines, we want really high saliency ratio, which is defined as a ratio of LD over LQ. Which means also it improves the difference between these two quantities. And there's different types of reluctance rotor. The most simple one is a salient pole rotor, which is similar to the example on the top, just with more number of poles on it. And then there are axially laminated reluctance rotors, where the laminations are shaped in this arc shape and they're stacked up together. And the flux has to go through the laminations, which will be the hard axis or the Q axis. And the flux passing in the magnetic material itself, it will be the direct axis. The most common one is the transversely laminated, meaning its laminations are taken and we stamp some holes in there to create air gaps and stack them together. This is the most easy to manufacture and more commonly used. So why synchronous reluctance machine? The most simple explanation is for this webinar, that's a good optimization problem because it involves several design variables and it often requires iterative design to fine-tune the performance. But putting that aside, there's also certain advantages for reluctance machines. One being that it's a very passive rotor with no magnetic or conduction material, and therefore the manufacturing and material costs are quite low, and it's also fault tolerant. It is also capable of delivering smooth output torque because of the AC sinusoidal excitation that comes with the stator. And also it operates at synchronous speeds, which gives a precise control on the operating speed compared to induction machines. It's also shown to have better efficiency than induction machines. For example, this is from an application note from ABB. They produced a IE5 synchronous machine and they compared the losses between these two. The main difference is coming from the rotor joule losses or the eddy current losses. In induction machine, there's a cage which conducts the current, and that's huge contribution to additional losses. But then along with that, there's still some challenges in synchronous reluctance machine. The first one is this air gap that are stamped onto the laminations. It's difficult to design them. There's no one good way to put that. And the saliency is limited, saliency ratio, which meaning that it cannot go to infinity. There is a certain limitation on how high it can go. Before we jump into the design itself, I want to define some terminology to understand what the shapes are called. So this light green material here is air gap, or that's the part where magnetic material is removed. We'll call that flux barrier. And there's always some bridges, either at the center or outside or in between, that structurally hold these metal together. Typically, it involves several of these barriers and not single. And that's because the saliency ratio and the torque output is dependent on this barrier shape and the number of barriers. The more barriers there are, the harder it is for the magnetic flux to go through, and the lower is the Q-axis inductance. And also the rib, or the bridges, the shape of those and the position of those define the torque ripple, which is defined as the range of oscillations comparing to the average value of the torque. So this is a torque waveform here. And with that, we can also see that based on various literature available, the barrier shapes can be quite simple, or they can get quite intricate and very complex depending on the nature of torque ripple and the torque performance we're expecting from the machine, as well as the speeds at which it has to operate without breaking apart. So sizing and initial design, this can be done analytically based on the power and voltage requirements. I'll not go much into the details here. There's a paper that's cited here that you can go through and find the equations. But basically the key point is these equations give you a rough estimation of the stack length and diameter, or the volume of the machine that you need to get a certain amount of power. Also, this is something you can do with JMAG Express, which is a tool in the JMAG family. And JMAG Express Online is actually a free version of the tool that's available. You can go to the website using the scan here and check for more details. But it is used to perform preliminary performance estimates, and it can also set up the initial model, and you can directly import that for a full FEA in JMAG Designer. For now, this JMAG Express doesn't offer synchronous reluctance machine, but one thing we can do is use a multi-layer IPM machine and turn off the magnets to bring it into JMAG Designer for full FEA. So with that, this is a initial design we started with, or we tried to design for. The stack length and diameter are 253.7 millimeters, which gives about aspect ratio of 1. It's a 48 slot, 8 pole, and we used 4 layer or 4 barriers per pole. And the lamination is 50 A1000, which means half a millimeter thickness lamination sheets. Operating condition of 4,500 RPM rated at 300 amp RMS. And the target power was 80 kilowatts. So starting with JMAG without using the JMAG Express, we can create the geometry from scratch using JMAG Geometry Editor. So this comes built in with the designer, or the JMAG FEA tool. And here I've laid down the basic barrier shapes with the geometry. And in order to control the shape of these during optimization, we have to assign some constraints to it. So here's a quick demo of adding the constraints. Basically, we'll pick a reference, pick the line or part geometry that we want to add a constraint to, and set the distance. And that will be a variable that can be controlled during optimization. I'll do the same for the barrier width as well. And also repeat that for the bridge thickness. So this process is repeated for all the barriers or all the geometric features, and more intuitive design dimensions. And the entire rotor can be defined with 26 geometric constraints. So once that is brought into JMAG Designer, this is the interface for JMAG Designer for the full FEA. And we'll be creating an electromagnetic analysis, transient analysis from the geometry. And then the default materials are all air. So we'll go to the material toolbox, search for the lamination that we want to assign. And to assign it, simply drag it and drop it onto the part. And in this case, the stator is laminated. So I'll enable the lamination part and assign a stacking factor there as 96%. And we can repeat the steps to assign appropriate properties for all the parts. So the phase coils are all copper, stator is the 50 A1000, rotor is the same with mechanical properties. Next step is to establish the analysis conditions. In this case, we're looking at transient electromagnetic analysis. So we'll switch to the conditions tab under the toolbox. The first one I'll assign is, since it's a partial model, we're using one pole, I'll assign that as a periodic model or periodic boundary. And then we want the rotor to be rotating, so we can simply drag and drop again and set the RPM. And this process can be continued for any number of conditions that are necessary. And in this case, for a synchronous reluctance machine, these are the only three conditions that we need. The rotation periodic boundary, motion condition, and the torque calculation of the rotor. Next step, we'll switch to the winding. JMAG has a built-in winding editor. So all we need to do is give it a reference starting position for the coil region, set the number of slots and poles, give the number of turns, and the coil pitch, and it'll automatically assign the winding pattern on the stator. We'll also add a circuit, but that's not covered here. But circuit is basically drag and drop into a circuit editor and assign link to this condition. That's it. And the last step before going to the structural analysis would be to create a mesh or refine the mesh. So in this case, we know the rotor is the key nonlinear area, especially the bridges. So I'll add some local constraints on the rotor mesh. For example, here on the rotor pot, I'll set it to 1 millimeter. And also, the rotor bridges are, I know they are thinner than 1 millimeter, so I'll assign one more localized edge constraint just to the bridges, and I'll set it to 0.25 millimeter, just to highlight where all the conditions are set. So all those bridges are at 0.25 millimeter. And then if generating the mesh, we can see here that the bridges are much more refined compared to the rotor, and rotor is a little more refined compared to the stator. I follow a similar process on the structural analysis, but here we only need the rotor because the centrifugal forces are acting on the bridges, and that's the key aspect we want to consider in optimization. And since there's only rotor, I went and created much more refined mesh on this one. Now the condition setup for the structural analysis, here we, again, as I said, we only need the rotor. So we'll go ahead and assign the centrifugal force, specify the RPM, and here instead of the rated speed, we can use the maximum speed that the machine is expected to work at. And again, since this is also a one-pole segment, we'll assign the periodic boundary condition. And for structural, the additional one is constraints and which boundaries can move and cannot move, so I'll assign that as well. So with that, I ran the electromagnetic analysis, and on the left here is the contour plot for magnetic flux density, and on the right here is the torque output from the FEA tool. So this model is giving an average torque of 121.9 newton meter with a torque ripple of almost 25%, which is quite high. And the output power at 4,500 RPM is only 57.5 kilowatts, which is quite short of the 80 kilowatt target. And then on the structural side, the analysis is performed at 12,000 RPM. And you can see on the left is the stress distribution plot. Typically, the material limit is about 420 megapascal, but adding some safety factor, we set the limit to 350 megapascal. And we can still see almost all the material and all the bridges are well within the 350 megapascal limit. And not just the stress, we are also looking at the expansion of the parts or expansion of the rotor and see how much the maximum displacement is. The air gap for this machine is 0.5 millimeters, so we don't want the rotor expanding too much and touching the stator. The limit on this plot is 0.1 millimeter, and we can see it's quite well within that, close to 0.04 millimeter. So observation from that is that the structural analysis shows the rotor geometry satisfies both the stress and displacement constraints, but the electromagnetic analysis shows that the rotor is quite saturated and the output power is way below the 80 kilowatt target. And also the torque ripple is quite high with over 20%. And then the requirements for us now are to improve the torque or power output to meet our 80 kilowatt target, to minimize torque ripple to less than 10%, while doing all this while maintaining the rotor geometry within structural constraints. And now if you remember the rotor geometry, there are 26 geometric variables, and there's a wide range of values that each of this variable can take. So with such wide possible parameter values, manually designing a optimum rotor or barrier shape that meets all these constraints is quite difficult. So this is where we'll more look towards an optimization, and I'll hand over the ball to Adarsh here.
Thanks, Dheeraj. Let me quickly start presenting. So thanks, Dheeraj, for establishing the need for an optimization. Before we go to the optimization, we need to understand a few concepts, and we need to understand how simulation process automation can be achieved before we can apply optimization methods on top of that. So we start with actionable models. And what are actionable models? They can be any of your simulation models, like the JMAG simulation that we just saw, or it could be any of your data models, or any analytical mathematical models that you already have that define your system, that could define your engineering process. So it is quite generic. So once you have an actionable model or multiple actionable models defined, you take that and automate and integrate it to define a process. Once you've done that, you come up with a well-defined actionable process that you can then apply various strategies on to explore the design space and eventually do a design optimization. So that's what this is telling us. So what are the different strategies that help you explore the design space, or help you do design space exploration in a guided manner? So you can apply DOE algorithms and then just sample the design space to get data, or you can go one step ahead and apply optimization algorithms, which are all available in modeFRONTIER, on the process that you have developed to achieve the objectives that you can define. Not only that, you can take the data that you generate and even use RSM algorithms to generate surrogate models that can be of use in various ways. So all of these methods help you discover innovative solutions in an intelligent manner. So to go a little bit deeper into how the automation of these processes or these workflows work, is that you take your different processes and treat them as black boxes. And essentially, this is what modeFRONTIER does. So all your CAD processes, CAE processes, or an FEA, CFD process, they all can be treated as a black box wherein you can feed in input variables that are free parameters and expect responses from that black box as a measure of the system. Now, once this is well defined, you can then define what are your input variables and what are your response variables that help you define your targets and objectives. So this is a snapshot of how a design optimization loop looks like. So here you see you have your various black boxes or your processes defined, and they could be either in parallel or in series, however you wish, whatever makes most sense and most efficient in terms of efficiency. And then you feed it various input parameters that you've parameterized within those processes and expect responses. And on top of that, you apply objectives and constraints that you would like to meet. And if you go through this one loop here for a given input variable combination, you come up with a set of values for all of these outputs. Then you ask the question whether you've satisfied your objectives or constraints. And you also ask the question whether you have exhausted all your computational resources that you thought you would use. If the answer is no, you essentially go back and repeat the whole process, and essentially repeat this whole process over and over again until you meet your objectives and constraints. And that essentially what design optimization looks like. Now, of course, keep in mind the number of input variables and the number of objectives and constraints essentially define the hardness of your optimization problem. Uh, Now, coming back to the problem at hand, we used a JMAG simulation that Dheeraj just explained to simulate the synchronous reluctance machine. And there is a JMAG direct integration node available in the modeFRONTIER platform that helps you connect to the simulation model that you have built in JMAG. And this video here essentially shows how that can be coupled with modeFRONTIER. So modeFRONTIER has a direct integration node for JMAG. You can simply drag and drop the direct integration node and point the JProj file where you have defined the JMAG simulation, and various parameters, the geometric variables and the responses are all parameterized within the model. And modeFRONTIER can then undertake a process called introspection by clicking the parameter chooser button. And modeFRONTIER can simply list out all the parameters that are available for inputs. And here you see that they can simply be made as input variables by dragging to the right. And similarly, we can drag the torque from the simulation, the estimated torque from the simulation, and the torque ripple measurement from the simulation as output responses by simply dragging them to the right. And it's as easy as that. modeFRONTIER is able to define your process automation workflow just by providing the parameterized JMAG model. Now the JMAG direct integration node has a lot of capabilities and options and features that the users can use, and they can run the JMAG simulation locally, or if they would like to submit the job to a high-performance computer where it's more efficient to run the simulation, you can directly do that through the JMAG node that's available in modeFRONTIER. Now, the workflow that we built to solve the problem at hand, essentially to get a better torque from the reluctance machine, and also to meet the constraints of the structural analysis, it looks something like this. So here we essentially had two JMAG direct integration nodes set up in parallel so that they can run parallelly in a more efficient manner instead of waiting for one to finish and then starting with the other simulation. But the good thing is they are essentially the same geometric models, and they share the same input variables, and modeFRONTIER can drive both of them at the same time. Okay. Now, if you look at these two nodes, one does the structural analysis, the other is the electromagnetic analysis. They are doing it in parallel. The responses from these two analyses are the structural responses, the von Mises stress, the displacement under the centrifugal force, and also the average torque produced by the machine and the torque ripple as well. Moving on to the optimization problem definition that we eventually ran after we completed the process automation workflow, we are essentially minimizing the torque ripple produced by the machine. We want that to be as low as possible. And we are also maximizing the average torque produced by the motor just so that the motor can be a high performance machine and it can meet the requirements that we need out of it. Of course, the design variables are the geometry variables that Dheeraj described that were set up in JMAG, and the ranges are essentially decided based on whether those ranges will provide us valid geometric configurations, and those are aided by the geometry constraints on the input variables. Because we do not want any inconsistency in the geometry when it's being generated. So these are essentially input constraints that can be defined in modeFRONTIER that assists in defining which region is the feasible region and which region is the infeasible region, for example. On the output side, we also have constraints on the stress analysis responses. So we have one misses stress defined so that it meets a safety factor. Also, there's a limit on the displacement that the rotor can undergo. We provided about 10% tolerance just so that it's easier for the optimization algorithm to get to the optimum region. There's also the torque ripple constraint that is defined such that it should not exceed a certain defined limit. So now, since we have in this problem, we have input constraints. We have essentially input variables that cannot have certain combination of values. So for example, here's in the 2D space, x1 and x2, there's an inequality that tells us, say, for example, left side of this line is an infeasible region. So when you have a lot of these constraints, and which is true in our case study here, we have a lot of these input constraints, it becomes very difficult to find even a feasible design point for the optimization algorithm to start with. So in order to tackle that, we started with a constraint satisfaction DOE strategy that helps seed the optimization run with feasible starting points. And the goal of this constraint satisfaction DOE algorithm, it's essentially to find combinations of input variable values that are all feasible to start with, and algorithm can get a head start in its design space exploration. This constraint satisfaction DOE algorithm is essentially implemented in modeFRONTIER using modified simulated annealing approach, and it is shown to be the fastest algorithm to converge towards the feasible region, even before an optimization is performed. And the added benefit of this algorithm is that it works both with continuous and discrete variables. So once we've defined the starting DOE set for the algorithm, we go about choosing an optimization algorithm, which is essentially the optimization strategy. We use the pile-opt algorithm that comes with modeFRONTIER. It's an ESTECO proprietary algorithm, which optimizes time and compute resources for a given optimization problem. It switches between local and global search as required in order to get to the Pareto frontier as efficiently as possible. And it has it does not need a lot of fine-tuning by the user. It works for most of your optimization needs. So for anyone who is new to the optimization world, they can easily choose pile-opt and try it out on their problem. So when we ran this optimization, just to recap, we have about 200 starting points that are got from the constraint satisfaction DOE. We ran about 20,000 iterations, and this was possible only because the individual simulations had a quick turnaround time. The structural analysis took about 42 seconds. The electromagnetic analysis took about 23 seconds. And we were able to get the results very, very quickly. So this is what we get in terms of the objectives as an optimization result. So these are all the designs that the algorithm explored in the torque and the torque ripple space. So the torque is on the y-axis and the torque ripple on the x-axis. You will see some of these designs are colored in green and some of these designs are colored in yellow. So what the yellow points mean are that those designs did not meet the constraints. Most of these designs did not meet the input geometry constraints, but eventually the algorithm was able to figure out the direction it needs to move to get optimal designs. In this case, you want to maximize the average torque. So you want to go to the higher top end of this y-axis. And for the torque ripple, you want to minimize it. So you want to go as close to zero as possible. So essentially, you want to go to the top left of this graph. And we will see that in the next slide when we zoom into the place that it converged. So here you see that when it converged, it got to the top left of the design space, and the red marked designs are essentially the best designs that are achieved by the optimization algorithm. They consist of they all make up the Pareto frontier, and I've filtered them out and plotted them separately here. We got about 27 Pareto frontier designs. Now, keep in mind the Pareto frontier designs are all equally optimal. That is because this is a multi-objective optimization problem. We do not combine the two objectives into a single objective. So the algorithm is able to come up with a trade-off between the two objectives, and it's up to the engineer who looks at the data to find out which objective needs to be at what level. So you can essentially make a choice as to what design you're going to go with by looking at this Pareto table. And that can be done by using a lot of different statistical tools and charts that are available in modeFRONTIER. So here we just plot the Pareto optimal solutions and looking at a parallel coordinate chart. Essentially, this is a chart that has all of the variables and outputs plotted in parallel to each other. And here I can apply the synchronize feature between the parallel coordinate chart and all of the other tables and charts that I have plotted. I'm just filtering out any designs that have a low torque and a high torque ripple, and that kind of narrows down to the design space where I want to be here. So essentially we can come down to about 4 choices or something like that, and we can take those points and further analyze it and try to find out if any of those designs are suitable to us. Now, just to make sure that the Pareto front that we achieved are not from different areas of the design space, and if there is a true convergence, we performed a PCA analysis and came up with the PCA transformed space. This is essentially all the designs from the optimization run plotted on the principal component axis from the PCA analysis. And I'm just looking at the Pareto designs marked in red, and you can see that all of them are kind of clustered together, and they are not kind of all over the place. And that kind of tells us that there is a convergence, and we can be sure that these are some of the best designs that we will achieve from an optimization run. So moving on from the optimization results, we filter out some designs, and then we move on to optimization solution validation. That's essentially going back to the JMAG simulation. And I will pass this on to Dheeraj now, who will go over some of these optimal designs and see how the results are.
Thank you, Adarsh. So yeah, as Adarsh was mentioning, so initially that the optimization program or process itself takes this as a black box, and it's looking at the input variables, and it's looking at the output values. So as long as the input constraints are met, and as long as the torque and the torque ripple and the displacement and stress limits are within the bounds, it keeps taking that as a valid design. And then those designs are filtered onto the Pareto front. So it is our responsibility to go back and look at those Pareto designs, and also to make sense of it. Is it a practical design that we can actually build, or does it make sense? So for that, we'll jump back into JMAG. So let me switch here. So this plots here on the left show the dimensions or the parameters that define the shape of these barriers. On the right here is an animation that's cycling through all the designs on the Pareto front, which are also on the x-axis here. So as you can see, there's not much difference between all the designs, and all the shapes look almost similar, which is all saved in from these parameter ranges. All of them, for all the Pareto designs, are within a range of a few millimeter. This defines the barrier height and the barrier width here. And also we can see is that some of them are quite settled down at the minimum possible values assigned for them. Particularly this flux guide between barriers 2 and 3 is very narrow, and this does not have any electromagnetic or structural significance. So basically it is converging towards a solution that almost nearly eliminates that flux path. So we picked one of the design from the Pareto curve, which satisfies a torque ripple of less than 5% and achieves maximum torque possible. And this design gives an average torque of 167.8 newton meters, which corresponds to 79.1 kilowatts at rated operation. And it has a torque ripple of 4.7%. Looking on the structural side, we see there's still within the structural limit of 350 megapascal. But we did notice that there's some portions of the outer bridges, there's still some excess material, which meaning that we can remove that and still survive within the stress limit. Now, as I mentioned before, these bridges need to be as thin as possible to improve electromagnetic performance. Otherwise, there's a leakage path for the flux. So what we did is we went back and updated the optimum design. We eliminated the thin flux path, which has no significance. And we also adjusted the barrier material there, or the barrier thickness, to create a modified optimum geometry. With that, repeated the electromagnetic analysis, and this is the torque waveform that's obtained from that. And the average torque is now 173.75 newton meter, which corresponds to about 81.8 kilowatts at rated operation. And also, this machine now has a torque ripple of 9.6%, which meets our initial requirement of less than 10% torque ripple. Also on the structural side, once again, looking at the stress distribution, everything is well below the 350 megapascal. So essentially, this geometry meets all our requirements. So that's one way to validate the geometry and get to where we need after the optimization is performed. So with that, looking at the possibilities of using this type of architecture or this type of workflow to other future models, one is to look at various rotor geometries. Here, in this case, we fixed the barrier shape based on 26 parameters, and it can only vary between those. But the barrier shapes, as I mentioned, can be more complex, adding more constraints, or even with the same geometric constraints, the shape can be different. Instead of a straight line, it can be an arc, and we don't know how that impacts the average torque or the torque ripple. So we can also parallelly check different shapes that are defined by the same geometric constraints. That's one way to expand the optimization problem. The second one is that for this case study, we were looking at rated operation at a single operating point. But often for traction machines, this has to be more as an operating range, meaning that there's a constant torque operation and then the constant power. So we can tie the JMAG model to a control algorithm, and we can determine the operating performance metrics at different operating points, which can all be considered in the optimization algorithm. And we can also add drive cycle analysis to this. So this plot here shows all these yellow points, which are drive cycle, are the performance points where the motor is operating in a city driving cycle. And we can also calculate, for example, say a net efficiency of the machine for this entire drive cycle, and include that as an objective in the optimization to maximize the efficiency for a given drive cycle. Similarly, this is in this case study, we're looking at structural and electromagnetic analysis, but we can also include, expand that to much higher level of in detail, including battery management, motor drive efficiency, cooling system, material cost, or noise, vibration, and harshness. And we can tie up all these. There's a lot of functionalities in JMAG that we can perform and tie all of these into constraints for the optimization algorithm and perform a multi-domain, multidisciplinary optimization. So with that, we'll conclude this webinar. And if you have any questions, as others mentioned, there's a Q&A box that you can type in, and we'll continue to answer the questions. Thank you.
Thank you. Thank you, Adarsh. Thank you, Dheeraj, for the excellent case study. This is Nachiket from ESTECO, and I'm just going through a number of questions that we have received, and I'll start reading through them and have the appropriate person answer them. So I think the first question is for PowerSys. How are the ranges of the input parameters determined?
Yeah, so this is Dheeraj, so I'll answer that question. Basically, in this case, we kind of went with what creates a valid geometry. There are some parameters where they coincide and might not create a valid geometry, but we included that still so as not to skip over those. But JMAG actually has a built-in rangefinder function that can run through these iterations. Once we assign, like give a maximum and minimum value, it will run through these iterations to give a possible ranges for those parameters.
Wonderful. Thank you, Dheeraj. The second question also is for the PowerSys team. How to calculate or define the torque ripple in a JMAG model?
I'm sorry, could you repeat that question, please?
Sure. How to calculate or define the torque ripple in the JMAG model?
Okay, so so what we did here is we took the torque waveform, and there is again a built-in function for JMAG where we can create a response value, which can be passed on as a result to either optimization or as even creating an internal post-processing calculations inside JMAG. It looks at the peak-to-peak variation of the torque, and it will calculate the torque average value from the torque vector or the torque array, and it will create the ratio of those. That's the ratio that is being passed on to modeFRONTIER here.
Perfect. Thank you, Dheeraj. The next one is for the ESTECO team. Was there an attempt to determine how robust the Pareto designs were to help decide which designs to go for?
Yeah, that's a good question. So that's certainly a next step that can be done after we arrive at an optimization result. So we can do what is called as a robustness assessment with respect to the results that we have. In this case, it can particularly be interesting just because we are dealing with a lot of different constraints. So if there is a little bit of a manufacturing issue that can deviate from the design value, then it can potentially be a problem in the performance of the design. Having said that, if one has the compute resources and the ability to run a pure robustness optimization by defining robustness objectives, by defining standard deviation based robustness objectives, that can certainly be a better approach in optimization. But in this case, we left it for the next step. We are just presenting the deterministic optimization case.
Thank you, Adarsh. This next question, I guess, can be answered by both teams, but an interesting one. Can the number of layers itself be used as a variable during this process, during the optimization process, that is?
Yeah, let me answer that for the initial part, and I think probably this, as I said, there's a two-step answer for this. So in JMAG, or in defining the geometry itself, the way we defined it, it is not possible to create that layer as a parameter itself. So we can't say 3-layer, 5-layer, and the geometry is automatically updating for that. Since we defined 4 layers and the parameters are defined for those 4 layers, we're only controlling those 26 parameters. But then again, maybe there's a good way to define the geometry which can be updated. So I think that requires the value to be an integral number, in a sense. There cannot be 1.5 layers or 2.5 layers. So that gets onto modeFRONTIER side. So then is that an input value that can be assigned?
Yeah, so with respect to, from the point of view of modeFRONTIER, variables can be either continuous or discrete, and it can modeFRONTIER can handle integer variables as long as defined in the model, and if the model can take those inputs within a well-defined integer range, modeFRONTIER can control them, and there are specific algorithms and strategies to do DOE and optimization using such variables. So yes, it is possible.
Okay. Another question, which I guess both teams can and touch on, the geometry problem that is defined here seems to lend itself to a topology optimization approach. Does ESTECO support this type of problem formulation?
Good question. I just said good question, and probably there's a delay in unmuting myself. So modeFRONTIER is essentially a parametric optimization platform. There are topology optimizers, but that can certainly be driven by modeFRONTIER through parameters that are defined that drive the topology optimization. In our current case study, we are purely doing a parametric study. It can also be looked at from a topology optimization standpoint. Yes, that's certainly possible. But for the current study, it was parametric.
Yep, and just to add on to that, from let's say all the domains can be defined based on material, and the material is a variable that can be assigned like the input constraint from the optimization, and JMAG is able to handle that part of the process coming in from modeFRONTIER. Topology optimization is possible with JMAG as well. So I think that clears up. Basically, we can assign those materials as variables for domains in JMAG.
Perfect. Thank you both, Adarsh and Dheeraj. Another question is, I think this was pertaining to the last slide, but which is asking about whether other analysis types can be added to the optimization process along with the electromagnetic analysis. So Adarsh, can you address this?
Yes, certainly other processes can be added to the process automation workflow that we have built. In this case, we are just looking at structural and electromagnetic analysis. We can also bring in other disciplines of the system and expand the scope of the problem to include other trade-off disciplines that might trade off with the objectives that we are looking at right now. So yes, certainly that can be done, if that was the question.
Yep. A few more. I think this is for the Powersys team. Is it possible to optimize the losses by skin depth and proximity effect by selecting proper number of parallel standard wires and winding wire diameters?
Yes, definitely. In this case study, we didn't do anything with the stator. We kind of designed it and we only optimized the rotor, but we can create individual strands in the stator coil instead of the lumped region that was defined in this example. And we can create skin depth mesh for each of those domains. And if the excitation includes PWM harmonics, then all the AC effects that are basically the proximity and skin effects, those will show up in the analysis. And now the next part of the question, if it can be optimized, I think that's more nuanced in a sense that it comes to the same problem as the number of layers in the rotor. Can we create the number of strands as an individual parameter? That's kind of comes down to how we set up the geometry itself. But then if we set the number of strands, and can we define where the strands are, the position of the strands, and the shape of individual strands, and how that impacts proximity and AC losses, yes, that can definitely be done.
Okay. Thank you, Dheeraj. I think this one is for Adarsh. Can you discuss about if there is an overhead in simulation time when you're running JMAG simulation through the optimization tool?
The overhead is essentially the amount of time JMAG simulation takes to come back with a result. And in this case, we had about, both of the analysis was under a minute per evaluation. So I would say when compared to some other problems that I've seen, it's not on the higher side. So the overhead is minimal, but that enabled us to run a lot of iterations of the optimization algorithm.
Thank you, Adarsh.
Just wanted to add to that. Since, as others mentioned here, we used parallel two nodes to run structural and electromagnetic. So in this process, the longest running simulation is what defines the total time, because the electromagnetic in this case is 23 seconds. So it's finished before structural. So the entire simulation time is dependent only on the structural analysis.
Excellent point, Dheeraj.
That's a good point. Yeah.
Yeah. I think this one is for you, Dheeraj. Is it possible to optimize the geometrical motor model with the high frequency switching components that are actually included in the inverter drive current?
Yes, it is possible, but we have to remember that once we add those harmonic components, we need to have sufficient time sampling to capture those frequencies. Typically, let's say for a 100 hertz fundamental, we'll be looking at 1 kilohertz switching frequency, for example. Then we need to define the time sampling based on the 100 kilohertz. So that'll extend or make the analysis time longer. That will obviously require more computational resources or computational time. That is the only barrier. Let's say if we're running 20,000 cases, and instead of 23 seconds, the electromagnetic analysis takes 2 minutes. That is a huge, almost a 10 times increase in the total analysis time. That'll be the only barrier, but yes, it can be done.
Thank you, Dheeraj. Another one, this one is for you, Adarsh. Are there any other optimization algorithms apart from NSGA2 and PyLopt in modeFRONTIER? Are there methods like response surface methods or different genetic algorithms that are there? And for this specific case, have those methods been compared? And which method does the team recommend?
Yeah, that's a good question. So yes, modeFRONTIER definitely has a lot of different optimization algorithms. Just generally speaking, we do not think that one algorithm can solve all the optimization problems that you may ever face. So there's always going to be some algorithm that may perform better on a given problem compared to another. So if time permits, we always encourage trying out different optimization algorithms on the given case. Having said that, not all optimization algorithms can be applied to a given situation just based on the different natures, different parameters of the problem, like number of input variables, whether the variables are continuous or discrete, whether the output variables are well behaved or are they very nonlinear. So in cases of nonlinear responses, as we had in this particular case, the torque ripple is nonlinear. Some of the RSMs may not do very well, so it becomes a little bit tricky in terms of what surrogate model you use for a surrogate model based optimization algorithm. So yes, we can certainly try other algorithms, but we honestly did not get a chance to run all of them. But that's certainly an approach that we can take in the future.
Okay, perfect. I think we are at top of the hour and almost covered all the questions. So thank you, Adarsh and Dheeraj, for your time, and all the audience for attending the session. One common question, as is always there, the recording as well as the slides from the webinar will be made available shortly, and there will be a notice sent out to everyone. Thank you again, and appreciate your time. Bye.
Okay.
Thanks everyone for attending.